In our previous video, we have talked about the theory part of binary search tree. Now in this video, we'll try to implement the binary search tree. Hopefully you have watched the previous video and understood everything from the previous video. Basically throughout this video, all we'll try to do is insert elements in a binary search tree. Now from our previous video, we have seen that using structure, we can actually represent our binary search tree in this manner. Now I forgot to mention one thing in our previous video, that was the root pointer. So in this case, 55 is the root node of our binary search tree. Now I'll declare a pointer and let's name this pointer root. Now from the name you can already tell that this root is going to point, this root pointer is going to point to the head of the binary search tree. So now root is pointing to the head of this tree that we have created using a structure. So the only task of this root pointer is to point to the root node of the binary search tree. Now let's talk about this scenario. Let's say we haven't created our binary search tree yet. So we haven't inserted any node inside our binary search tree yet. Now who the root pointer is going to point to in this scenario? As there are no nodes available yet, we'll just assign null to this root pointer. So null in this case will refer to the fact that there are no elements in the binary search tree. Now on the left side of the screen, we have drawn the binary search tree that we are actually given, and on the right hand side we have actually represented that binary search tree using structures. Now let's assume that we are given this value 34 and we are asked to insert this value 34 inside our binary search tree. Now in order to insert the binary search tree, what do we need to do? Obviously we will have to insert this node as a structure, and therefore to insert a node inside the binary search tree we will have to first create a structure. So let's say this is the structure. Now I'll have to put the value 34 inside the structure, so I'll just write 34 in this case. Now we have just created this structure. We have just created the structure which contains value 34, but it doesn't have any left child or right child yet, and therefore we are going to assign null in this case. So null means that this node 34 doesn't have any left child or any right child. Now why have we assigned null? Because we have just created this node 34, and as this node 34 is just a new node, that means that this node 34 doesn't have any right child or left child yet. Now let's start trying to insert this node 34 inside this binary search tree. So I'll just drag and drop it here. Now let's have a look at the root pointer. Is root pointer null? As you can see, root pointer is pointing to a structure, so that means the root pointer is not null. Now the value inside the root node is 55. And the value inside the newly created node is 34. Now 34 is less than or smaller than the root node 55, and therefore we'll go and check the left child of this root node. Now we cannot yet insert 34 as the left child of 55 because the left child or the left pointer of this root node is pointing to a structure. So that means the left pointer of this root node is not null, and that means that the root node has a left child. So basically we cannot insert 34 as the left child of this root node, and therefore we'll have to compare the left child of the root node with the newly created node 34. Now as you can see, 34 is smaller than 40, so that means we will have to insert 34 as the left child of the node 40. So let's drag and drop it here. But when you come here, we can see that the left cell of node 40 is not null. That means the left cell of this node 40 is actually pointing to a structure. So that basically means that 40 has got a left child, and therefore once again I'll not be able to insert 34 here. Now let's compare these two nodes, 34 and 34. Now 34 and 34 both are equal. As 34 is less than or equal to the node 34, therefore we'll have to insert the node 34 as the left child, and therefore I'll just go to the left of this node 34. Now once again the left cell of 34 is not null. The left cell is pointing to another node, and that means the 34 has got a left child, and therefore once again we will not be able to insert in this place. Now once again I'll compare the two values 34 and 28. Now the node 34 is greater than the node 28, and that means that we'll have to insert the node 34 as the right child of node 28. Now let's now place 34 on the right side of the node 28. Now if we check the right cell of node 28, now the right cell of this 28 is actually null. That means that node 28 doesn't have any right child, and that means that we can finally put 34 as the right child of the node 28. Now the right cell of this node 28 is no longer going to be null. This time it's going to point to the newly created node 34. Now let's refresh this step once again. Why were we actually able to insert node 34 in this case? because when it's checked the right cell of node 28, it was null, and null means that node 28 doesn't have any right child. Now if it doesn't really have any right child, then that means that we can finally put 34 as its right child. Now if you are to place this node 34 in this binary search tree, then it would be put just right here. Now we'll do the same thing in our code as well. Now let's start writing our code. Now what should we do first? We can actually make a template for all these nodes. So I'll just go into the code and write struct node. I'll just write node as the name of the template of all the structures here. Now all of these structures can hold one integer data. So in the template of all the structures, I'm just going to declare a variable int and let's name it data. Now the other cell of this structure is going to hold a pointer. Now this pointer can point to any other structure of the template node. Now I'll try to help you memorize the basics of pointers in case you have forgotten those. Now if your concept on pointer is really strong, you can skip ahead to. Now let's talk about this piece of code, int asterisk data. Now this asterisk means that this data is a pointer. Now what type of value is this data actually going to point to? As we have written int here, it means that this data pointer can point to an integer value. So this data pointer can point to any integer values like 1, 2, 3 or something like that. Now if we wanted this data to point to a float type of value, maybe 1.4, then instead of int we would just have to write float here. Now from this graph, as you can see, these are all pointers. So all of these cells are actually pointers. Now the same thing also holds for these pointers as well. In this case, all these pointers are actually going to point to a node, and therefore instead of int asterisk data, we'll just have to write here struct node asterisk data. Now struct asterisk data means that data is a pointer and it can only point to those structures who have got the templates of the structure node. So it cannot actually point to any other structures. It can also only point to the structure those are of this template node. So basically these pointers, as you can see, we are going to implement these pointers using this piece of code, and therefore we'll have to write here struct asterisk node left and struct asterisk node right. Now node left and right, these are actually two pointers which can point to structures. Those are of type struct node. Now the next thing we'll do is declare this root variable. Now what does this root variable do? The sole purpose of this root variable is to point to the root of this tree. So that means it's just going to point to a structure, and that means we'll have to just write here struct node asterisk root. Now if you can remember from linked list, you just name it as head instead of root. Now from our previous discussions, we know that initially there are no elements in the tree. So that means that there are no nodes that the root can point to. So we'd assign null to the root. Null in this case means that the root is not pointing to any element or the tree is empty. So in our code, we'll just assign null to the variable root. Now it means that initially there are no elements in our binary tree at all. Now let's try to implement the insert function. We'll just write void insert. It will take the value of a node as its parameter. Now let me show you how the insert function is going to work. So I'll just call it like this. I'll just say insert, let's say 55 as its value, then 40, 80, 34. Now whenever I'll say insert 55, so it's going to create a node with the value 55, and it will insert this node in our binary search tree. The same way it's going to insert 40, 80 and 34 in our binary search tree. So that's how the insert function is going to work. Now to achieve this task, we'll have to do one thing. We'll have to first create a node just like the way we created the node 34, and then we'll have to assign null to its children because it doesn't have initially left or right children, and then we'll have to insert it into our binary search tree. Now back to the basics of pointers. How do you create a node? And by creating a node, I mean creating a structure like this which has got a data field, a left pointer and a right pointer. Now all we need to do is write this piece of code to create a structure like this. Now don't forget that we have got this structure declared outside of our main function. Now let's try to see what this malloc function does. we have called this malloc function here. So basically it will go into our heap memory. So let's say in this case this is our memory. Now this malloc function will go into the memory and create a block of space for us. So let's say this is the space that the malloc function has given us. Now the size of this given space is actually going to be the size of the struct node, as we have specified struct node here. So we have specified size of struct node, and therefore there will be actually 3 fields inside this space or inside this structure. Now this field will hold data for us, and these 2 fields are actually the pointers that will be referring to the left and right child. Now that's how pretty much this malloc function works. I cannot go into more details in this video. Now after creation of this space inside the memory, obviously it has got a memory location. Let's say the memory location for this space is 10. Now after creating the space or the structure we have specified here, this malloc function will return the address or memory location of that structure or of that space, and we are assigning that value. As you can see, we are assigning that value to another pointer, and that means that new node is a pointer. If new node is a pointer, it will now point to this structure. Now that's how this line works. It will create a structure for us, and new node will be pointing to that newly created structure. So I'm going to copy the same line inside our insert function. Now let's see what have we done so far. As you can see, so far we have assigned null to the root. It means that root is assigned to null. It means that there are no elements inside the binary search tree. And then we have written this line, so it will just go inside the memory and create a node for us. It will look something like this. Now this is the data field or value of the newly created structure. Now to assign value in the data field, we'll have to just write new node dot data is equal to value. Now inside the main function, I have called the insert function and passed 55 as the parameter, and that means the value of this variable value is going to be 55. Now here the value is assigned to the newly created node or to the data field of the newly created node. So that means we can just write 55 in the data field of newly created node. Now I'll have to assign null to the left and right child, and therefore I'll just write new node dot right is equal to null and new node dot left is equal to null. So let's try to rephrase again. So I've called this function insert and passed in 55 as the parameter. So the value of this variable value is going to be now 55. Using this line, we have created a new node. So this line of code is going to create a new node in the memory for us, and then I have assigned this value in the data field of the newly created node. So 55, we can write 55 in the data field here, and then I have assigned null to the left and right child of this newly created node. So it will be pointing to null, and so this one will also be pointing to null as well. Now all that's left to do is just insert this node inside the binary tree. Now initially there are no elements inside the binary search tree. Root is pointing to null, and that means if we insert our newly created node, this is going to be the one and only node inside our binary search tree, and that means that root will be now pointing to 55 as it's the only node inside our binary search tree. So we'll make root point to the node 55. But one thing we'll have to remember, that this will happen only when root is null, only when there are no elements inside the binary search tree. So let's write it down inside our code. If root is equal to null, we'll perform this task, else we'll have to do something else. So inside the root is equal to null statement, we'll just write root is equal to new node. Now after execution of this statement right here, root will no longer be null and root will point to the newly created node or new node. Now our binary search tree will look somewhat like this. Root will point to the 55 to the node 55, and the left child and right child of node 55 are null in this case. Now insertion of the node 55 is done. Now we have called this function insert 40. So this time we have passed 40 as the parameter. Therefore the value of 40 is going to be 40, and this line will create a node for us, and 40 will be inside the data field of this node now. And as you can see, left and right child of this newly created node will be null. Now if root is equal to null, as you can see from the graph, the root is no longer null, the root is pointing to something else. So that means this if statement will now not work. It will go inside the else condition. Now inside the else part, I will create a temporary pointer and name it temp. Then I will assign root to the variable temp. So that means now temp will be also pointing to the root node. Now if you can remember from our earlier discussions, when we are trying to insert this node 34 inside this binary search tree, we had to first go to the root node 55 and then we would compare the values, and as 34 is smaller than 55, then we would go to the left child, then to the left child once again, then to the left child once again, and as 34 is greater than 28, in this case we would check the right child and find out that the right child is null, and that's when we actually were able to insert the value 34. So basically we had to traverse a lot, and we are going to traverse using this variable temp here. So temp will first point to this root node, and if it is the value is smaller, then temp will go to the left child, then if it is again small, then temp will left to the left child, then left child once again, then it will go to the right child. In this case the right child was pointing to null, so it will be pointing to null, and in this case temp will also be null because it doesn't have any right child, so temp will be null. So when the value of the variable temp becomes null, that's when we'll realize that we can now insert the value or insert the node. For that reason I'll take an infinite loop, and this loop will break whenever the value of temp becomes null. Now this is the graph that we have currently got. Temp is pointing to the root node. Now we'll have to compare these two values, 40 and 55. If 40 is less than or equal to 55, then we'll have to go to the left child, and if 40 is greater than 55, then we'll have to go to the right child. Now I'll have to do the same thing inside the code. Now to access this variable 40 here, or this data field, I'll simply write here if new node dot data. So new node dot data is actually this data right here, and to access this data field I'll have to just write temp dot data. So I'll just write here temp dot data. Now if new node dot data is less than or equal to temp dot data, then we'll have to go to the left child. So we'll just go to the left child, else we'll have to go to the right child. Now let's say this is our graph right now, and this node right here has got a left child and temp is pointing to this node. Now to access the data field, what did we use? We just simply wrote temp dot data, and therefore to access this field we'll have to just write temp dot left. Now as 40 is less than 55, that means in this case this first condition is going to be true. So 40, as you can see, 40 is less than 55, and if first condition is true, that means we'll have to go to the left child. So basically now we'll have to do something that will make this temp point to this node instead, this left child instead, and to achieve this we'll just simply write temp is equal to temp dot left. Now how does this work? Now as you can see, we can access this field using temp dot left. So basically this field and temp dot left are the same. Now this field is pointing to this node right here. It means that temp dot left is also pointing to this field right here, or to this node right here. And here I have assigned temp dot left to the variable temp. So this statement will basically say temp to point where temp dot left is pointing to. Now temp dot left is pointing to this node. It means now temp will no longer point to this node, temp will now point to this node. Now let's assume that the value here is not 55. Let's say the value here is 10. So in this case 40 is actually greater than 10. It means that it will actually go to the else statement, because the value that we have got inside our newly created node is greater than where temp is pointing to. So that means that we'll have to go to the right child instead. So now temp should not be pointing to this root node, temp should be pointing to this right child of this root node. Now we can actually access this field using temp.right. Now this field is pointing to this node right here. That means temp.right is also pointing to this here. So I'll just set temp to point where temp.right is pointing to. So inside our code, we'll just go and copy this line and just write right here instead. So I'm telling temp to point to where temp.right is pointing to. Now after execution of this line, temp will no longer point to this root node, temp will now point to this node. So now let's see how it works. Initially I said temp is equal to root. So basically it means temp is now going to point to the root node. So I'll just write here temp is pointing to this root node. Now we'll compare 55 with the node 40. Now 40 is less than 55, so that means the first if statement is going to get executed. So temp is equal to temp.left. So in this case, temp will now go to the left child. So now temp will point to this child. Now what happens next is it's going to go to the while loop once again, and actually this while loop is going to run for infinite times, as we have not specified any condition for this while loop. Now once again it's going to compare the values of new node and values of temp node. Now temp is pointing to this node 40 here, and new node is pointing to this node, and the value that we have got here is 40. Now once again this value 40 here is less than this value 40 here. It means that this if statement is once again going to get executed. Now in this case, this is our temp and this is our temp.left, and temp.left is pointing to this node, and that means that temp will now come and point to this node. Now that's how this while loop is going to work actually. Now all that's left to do is give a condition that will break this loop. Now let's say somehow this node right here has got no left child, so it means that the value of temp.left will be null. So the value of temp.left right here will be null. Now as this value and this value both are equal, we'll have to go to the left child as per this statement here. So we'll assign temp is equal to temp.left. Now the value of temp.left is null, so that means the new value of temp will also be null again. So before going to the left child, we'll have to first check whether or not the node the temp is pointing to has got a left child or not. If it has a left child, then only we'll go to the left child. If it doesn't have a left child, then all we can do is actually make this new node that we have created its left child. So we'll, in this case, as this node has got no left child, so we'll make this newly created node its left child. So first we'll check if it has a left child, and how to actually check that, and how we actually check this. If the value of this left child is null, that means it has got no left child, or else it has got a left child. So I'll just write this piece of code. I'll just remove this line, and instead I'll just first check if it has got a left child. So I'll just write if temp.left is equal to null, so it means it doesn't have a left child, and else it means it has a left child. Now if it has a left child, then we can go to the left child. So I'll just write temp equals temp.left, and if it doesn't have a left child, then we'll make this newly created node its left child. So we'll just write temp.left is equal to new node. Now in this case, temp.left is actually null, so it means that it will come to this if statement and it will execute this line of code. Now basically this line is saying, all this line is saying is point temp.left to where new node is pointing to. Now new node is actually pointing to this node, so it means that temp.left will now point to this node. So now our graph will look somewhat like this. Now we can say we have actually inserted the new node. Now that we have inserted the new node, that means we have nothing left to do, and that means it's time we break this while loop. So I'll just write break here, and the same thing is also going to happen for the right child here. Now let's say we've got this small graph and we want to insert this value 10. Now temp will first come to the root node and compare 5 and 10, as 10 is greater than 5, so it means temp will now go to the right child. So temp will now point to this node 9. Now 9 and 10, so 10 is greater than 9, so again we'll have to check for the right child, but it has got no right child here, so that means that it's time we put 10 as its right child. So we'll just write 10 here. So basically we'll have to handle the things the way we dealt with left child. So I'll just copy all these things from this left child and paste it in here. Now if right child is null, that means I'll insert this new node as its right child and break, or else I'll have to go to the right child. So this is how this insert function is going to look like.